my screen.
For watching this video.
Oh, thanks.
This demo is about vulnerabilities that exist in network drivers while processing device IO control requests. It is currently believed that these vulnerabilities may lead to only local privilege escalation exploits. I will show you that it's not always true and they can be exploited remotely. I will use three systems during this demo. This one is a sniffer to watch in Wireshark injected frames. It is listening on the channel 6. This laptop is a Tigers system. It runs PuckTrack Final and it has a wireless interface configured for raw injection. It also has a exploit code that will send many malformed beacon frames with oversized SSID elements. This system is the target system. It has Intel Pro Wireless 2200BG network adapter with old version of W29N51.sys driver. I have modified this driver to introduce the vulnerability that we are discussing during my presentation. And this system will be exploited remotely. Again, the vulnerability I will exploit is fake and exists only on this laptop.
The wireless is on and the driver is receiving some frames. I will run IO control fuzzer to show that in the absence of specifically crafted wireless frames, the driver doesn't crash after receiving request for BSSID list object identifier. Let's first run IO control BO utility to discover device name of target device. It's Intel Pro Wireless 2200BG network connection. Let's run our fuzzer in NDIS mode against our device. We'll send object identifier 0D010217 and buffers large enough to contain information about all discovered wireless networks, let's say 10,000 bytes, filled with small a's. And we'll log results into the log file, including buffers in verbose mode. Let's run it. Alright, it's finished fuzzing. Okay, we see the fuzzer sent IO control NDIS query selected stats and requested for BSSID list object identifier. Here's the contents of the input buffer before request filled with small a's, and the output buffer before request. And then we received the response from the driver. You can see the contents of the output buffer after the request. It contains information about all discovered BSSIDs. You can see the SSID of discovered lands, guessed, default, and so on. So the driver returned 9,000 bytes correctly and didn't crash.
Let's inject some malformed frames. We'll use this laptop and we'll inject a bunch of malformed beacon frames containing SSID elements filled with all A's. The total size of each malformed frame is 70 bytes. And we'll see what we got on the sniffer system. Some amount of beacon frames we filter by the destination address. Alright, so this is the SSID element consisting of all A's, which is 41 hex. So we're receiving some frames. I turned off wireless so that we did not get any crash while describing the injection and sniffing. But now I'm turning wireless on. This will trigger the scan for the available wireless networks, and the wireless management application, user mode application, will request the WLAN driver for discovered networks and will send object identifier BSSID list, which contains a vulnerability, and we'll see this. Alright, we got the blue screen, driver IRQL not less or equal, and it's we clearly see that the stop has parameters that are sent within the malformed frames or injected by the attacker. So let's dump the memory. Okay, we've finished dumping memory. Let's reboot this laptop.
Let's open this crash dump in Windows Debugger. Here we go. Take a look at trap frame contents. Both instruction pointer and base pointer registers were overwritten with the data we injected within malformed beacon frames. Let's inspect call stack. It shows that default occurred in miniport query information function. This is required for all ND's miniport drivers function and is used by NDs to query miniport for object identifiers. It was called with OID D010217, which is BSSID list. We learned two things from this dump. First, the vulnerability depends on the data we injected within malformed wireless frames remotely. And the second is that the vulnerability occurred in the functionality processing local request for BSSID list object identifier. It's exactly where we introduced our fake vulnerability.
We have just seen that local vulnerabilities in the device I/O control interface of network drivers are not always local and can be exploited remotely by the attackers. That's why they are as dangerous as any other remotely exploitable vulnerability. Thank you very much for still listening to this demo, and we'll see you in Vegas. I apologize for the bad quality of the video and sound, and Thank you. I appreciate that you're still listening to my talk. Thank you very much. Any questions? We have 5 minutes. The question was, what's the best way to detect these before the crashing the system, these kind of vulnerabilities. So basically, when you are trying to discover the vulnerability in the remote interface, you will most likely crash the system. So let's run that in the VMware workstation, or so you cannot you don't need to reboot each time and your system. The local vulnerabilities are not necessarily crash the systems. So the local vulnerabilities can corrupt the user mode buffers, and that indicates that the driver does not process correctly the buffers, but it doesn't crash the driver. So if you change the state of the driver, some specific condition, then the driver may crash. With the remotely exploitable local vulnerabilities, it typically crash the driver and the system. So we can use static source code analysis to identify them without crashing any driver. But the fuzzing of kernel mode implies that you will crash something. Yes, you may install the wireless IDS that will trigger some kind of alerts while observing malformed frames. For example, filled with NUPSLAD or some other heuristics. So you can identify those kind of attacks and prevent from them, actually. It doesn't depend on the frame type, subtype, or the information element. You can the wireless IPS should be able to prevent exploits sent within any wireless frame. So it's not depending on the SSID or beacon frame. Well, this vulnerability wasn't found. I introduced it myself. It's a fake vulnerability for this demo purpose. Yeah, I knew where the vulnerability is, how to exploit it, and I exploit it using the exploit code. It's not the fuzzer, actually. It's just an exploit code. Well, they may be found. All the examples I demonstrated in this demo are based on real code. Not the real code, but based on the real vulnerabilities we encountered in the past.